This is going to be the video for differential equations section 8.2, the second day. And in the first day of 8.2, we talked about what an eigenvalue and a corresponding eigenvector is. And we talked about how we can use those things to solve a differential equation system. And we restricted ourselves to the case where that characteristic equation produced eigenvalues that were each unique, distinct real values, which will frequently happen. But because that characteristic equation is kind of like an auxiliary equation that we saw earlier in the course, remember there were other cases where sometimes we had distinct individual real values, but other times we had repeated real values or we had complex values. And so we're going to talk about that here because that can happen with the characteristic equation for eigenvalues as well. You can have distinct real eigenvalues for a coefficient matrix, or you can have repeated real values, or you can have complex values. So we're going to handle in the second day here the case of repeated eigenvalues. So a distinct real value that's repeated. How do we handle that? All right. So we know that. Well, that's just what I was just saying here. So we know that that you get, if you have distinct real eigenvalues, you form the general solution by superposition of taking each one times a corresponding eigenvector, and then you take a linear combination of all of those with the different generic constants multiplying. Okay, but we can have repeated roots. Okay, now sometimes if you have an eigenvalue, that a single repeated eigenvalue, you can actually find more than one eigenvector to go with that. Now we know that you can find an infinite number of eigenvectors by how you choose K3, let's say, right? But what I'm saying is that in some cases you can find two linearly independent eigenvectors that go with a single eigenvalue. Okay, so let's look at an example here, and we'll see what we mean. So let's say we have a three-dimensional system here where we have x prime equals this 3 by 3 matrix times x. So we have an x, y, z here, independent variable t. We start by finding the eigenvalues for the system by subtracting lambda from the main diagonal of the coefficient matrix. And then we carefully solve this determinant equals 0. So we have this times the determinant of this times this minus this times this. That's this part here. And then we have this, so the negative of this value times the determinant this times this minus this times this. That's what's going on here. And then we also have this last one out here. So 2 times the determinant of this times this minus this times this. So you're always eliminating, the column and row of the multiplier that you're using. And if you carefully multiply all that out and combine like terms, you get this differential equation, or this characteristic equation here. It's a third order equation for lambda. We can factor out the negative to get that it's negative, and then this x cubed minus 3x, or lambda cubed minus 3 lambda squared minus 9 lambda minus 9. And so you have to somehow factor that, or there's no quadratic formula for third order, but we could also try synthetic division if we can guess. So maybe we try guessing some values. I'll show you an example of that with synthetic division. Maybe we end up trying -1. Let me show you that does work. If you try -1 here and use the coefficients here, so we've got 1, -3, -9, -5, then you could do synthetic division here and get that that's what, -4, so this becomes 4. So this is going to end up being -5, and when we multiply, that's 5. So this gives us a remainder of 0, and that gives me the equation lambda squared minus 4 lambda minus 5 left. So you test and you find that -1 works as a 0, so we can factor out an x minus -1 or x plus 1, and what would be left is lambda squared minus 4 lambda minus 5, right? And then that further can be factored into lambda plus 1 times lambda minus 5. So in the end, we have lambda minus 1 squared, right, times lambda minus 5. And here's the problem, right? We have a three-dimensional system, so we really need 3 eigenvectors, but we only have 2 unique values. We have lambda is 5 and lambda is -1, but the lambda is -1 is repeated. It has a multiplicity of 2. All right, so that we're going to have to learn how to deal with that case. Okay, so maybe first we could just go ahead and work with the one that does work, lambda is 5, and just review the procedure to find the corresponding eigenvector, right? We would go ahead and say 1 minus, and we'll plug in a 5 for these lambdas here, and we'll get, so -4, -4, -4 on the main diagonals. And when we fill in all of that with the 0 on the right-hand side, we get this matrix, right? So we're taking, we're really solving this equation for the k that goes with that lambda. We fill in this lambda here, and then we plug the lambda in, and then we solve this system for the values for k that make that true. We've got this, after RRAF produces this, typically the last row cancels, and we were able to write k1 and k2 in terms of k3. So k1 is k3 and k2 is negative k3. So that means we have general form, whatever we choose for k3, then k1 will be the same and k2 will be the negative. So for example, we could choose 1, and then we would have 1, -1, 1, or we could choose 2, and we would have 2, -2, 2, or any number here, right? So while all these are okay choices for the eigenvector, right, they're not linearly independent of each other because they're all multiples of another. So if I choose this one is not linearly independent because it's just this multiplied by 2. So I'm only going to get one linearly independent eigenvalue from that, or eigenvector from that eigenvalue, right? Because both of these are dependent upon this k, okay? So we got one eigenvalue. It doesn't matter which one we pick, but I can only pick one of those. Okay, let's take a look at the other eigenvalue, 2, -1, one that had multiplicity 2. Well, in this case, if we subtract 2 here, right, then we're going to get this matrix to solve with the 0 on the right-hand side. We get this, and then an interesting thing happens, right? Not only is the last row canceled, but the second row cancels as well when we do RRAF. And that means we just have one equation, k1 minus k2 plus k3 is 0. So I can go ahead and solve that for k1, but now k1 depends upon both k2 and k3. And what that means is that I can choose different values for k2 and k3 and find the corresponding k1. So for example, I could choose k2 to be 1 and k3 to be 0, and then compute that therefore k1 has to be 1. But I could also choose k2 to be 1 and k3 to be 1, and therefore k1 would turn out from this equation to be 0. And these two are not linear multiples of each other, right? So these ones are linearly independent. So these are effectively two separate linearly independent solutions from one eigenvalue. So this doesn't happen very often, but it can happen. It happens in this case where both of these rows cancel. Right? And then what I could do is form a solution where I have one term for the 5 using its eigenvalue. And then for the -1 value, I can use both of those separate eigenvalues, 1, 1, 0, or eigenvectors, 1, 1, 0 and 0, 1, 1, with their own constants, because those two are in fact linearly independent from each other. All right, so that can happen, and that's nice that that happens. It's less work than what I'm going to show you have to do more generally, but most of the time that doesn't happen. More commonly, you're only able to find a single linearly independent eigenvector to go with a particular eigenvalue. So instead, let's think about how we can handle this. When this happened back with the single equation, with the standard auxiliary equation, we ended up just taking the same value, but we multiplied by an extra x. Okay, so we're going to do something similar to that, but it just turns out to be more complicated. So I'm going to show you the result, and then I'll show you a derivation about how we show that this is true. So we're going to take these single, let's say we have a multiplicity of 2 eigenvalue, which is lambda 1. So we include one term with its own constant c1 for that value. And then for the second term, we do c2 times the same eigenvector, but times t e to the, so we put an extra t in there with the lambda, but plus another eigenvector that we're going to call p with the original e to the lambda without the extra t. Okay, so we're going to postulate that would be a solution, and then I'll show you what's required of this p to make sure that that does in fact work. So this is going to be the form for writing up repeated roots, multiplicity 2, and then we'll show what we have to do to get that p vector. All right, so let's assume that that is the form the first solution is this form, but the second solution is this form, like that, then we can take the derivative of this structure to find what, let's use this from here on down, okay? If we postulate that something's in the form kt e to the lambda 1t plus p e to the lambda 1t, which was the part of the parentheses, that would be the form for the second solution, this right here. We're going to show that this can in fact be forced to be a solution by taking the derivative of that. And this first term is going to require product rule because we have both multiples of both of these factors include the variables. So kt first times derivative of the second plus second times derivative of the first. And then this doesn't require product rule to take the derivative. We just take the derivative of the exponential, which multiplies by the lambda. Right, and rearranging the terms a little bit, we can pull off the t1 separate, just to factor out this lambda over here. If we then substitute this in for this in the system, that's going to equal a times the original x. So if we substitute in, here is x prime equals the coefficient matrix times x. That's substituting back into the system. Then if you carefully get all the terms on the left and factor things out, you can regroup so that you have this multiplier times t e to the lambda t, and this multiplier times just e to the lambda t has to equal 0. Now, the only way that that can be 0 for all t is if individually each of these two expressions are both themselves 0. And so this one on the left is the expression that we use to find an eigenvalue, right? If ak minus lambda k equals 0, then that will be true if this is an eigenvalue and this is the corresponding eigenvector, right? So that means that whenever we solve, we start by finding that this term is going to be a regular eigenvalue. The question is, what happens if we have to have this equal 0 that lets us to establish what the p is? So ap minus k minus lambda p has to equal 0, looking at this right now. And if you were to move the k to the other side, you could factor out the p here, and you would have this expression, a minus lambda ip equals k. So what that is that's like saying you would use the same methods to solve for an eigenvector. P is like an eigenvector, where we use that same repeated eigenvalue, except that instead of a 0 on the right-hand side, instead of a 0 vector, we're going to use the eigenvector that we calculated first as the new right-hand side. And if we do that, then that means that this structure that we showed back here will in fact be a second solution that we can combine with the original solution, and it will be independent. Okay, so this is kind of like just a derivation to show that basically this p here, use a different color, this p is a new eigenvector that was calculated, but when we do the calculation of the right-hand side, we put in the k vector that we got when we established this one. We use this k to calculate what the p vector is. Okay, so it's again always easiest to see this with an example. So let's look at an example. Here we have a solution. This is just 2x2 equation, so we have a system. We're going to go ahead and find the eigenvalues for this system. So we've got, we subtract lambda from the main diagonal. We compute the determinant and set it equal to 0. We get this equation, which happens to factor into lambda plus 3 squared equals 0. So there's a single eigenvalue of -3, but it's got a multiplicity of 2. Okay, so first we'll find a corresponding eigenvalue to that by taking that -3 and subtracting it in the main diagonal. So we're going to get 3 minus negative, so plus 3, that's 6, -18, 0. And at first we go ahead and use the 0, 0 on the right-hand side. That's what we do when we find eigenvalues or eigenvectors. And then we do our REF, and we get that k1 minus 3k2 is 0, or k1 is 3k2. This is the form for the eigenvector, and so maybe we choose 1 for k2, and therefore this has to be 3. So we've got this eigenvector here that corresponds to lambda equals -3. Okay. Now, unfortunately, we didn't have that case where we're going to be able to get a second vector, right? I could choose 2 here. I could choose, 2 and make that 6, but that's not linearly independent. So that trick that we saw before didn't work. We're going to have to use this other method. So to get the P vector, the second eigenvector, we're just going to redo this procedure. Let me use red. We're going to redo this procedure. The only thing is we're going to replace this 0, 0 with the 3, 1 that we got the first time. So we use that same exact matrix over here, except using 3, 1 on the right-hand side. Okay, we go through the process of RRAF. We get a new equation here, which says that, now these are our values for P. So it's P1 minus 3P2 equals 1/2. And then P1 is therefore 3P2 plus 1/2. So I could choose, for example, 0 for P2, and P1 would be 1/2. You're not allowed to choose anything that would give you 0, 0, but you're welcome to choose 0, 1/2, right? You just have to have a vector with some length, right? So 1/2, 0. Then what we do is we plug that into the general solution form. So the general solution form is, first we build a term with C1 with the original vector. So that's going to be C1, 3, 1, e to the negative 3t, because the lambda was negative 3. And then for the second one, we say C2, and in the parentheses, we use that same 3, 1, but times t e to the negative 3t. There's where we're introducing our extra x value, right? But then we add this new p vector times the original e to the negative 3t. Okay, and we showed in the last screen why this whole thing is in fact a valid solution as long as we've used that eigenvector procedure to find the second p vector. Okay, so that's how we get a repeated eigenvector to produce a second value. We do the procedure again, but we replace the right-hand side with the eigenvalue that we used in the first part, whatever we chose. All right, so that's the procedure, and this is extendable to higher orders, right? It gets harder because the determinant gets harder to find. And that means, but I just wanted to show you that this could be true for multiple vectors as well. Let's say you had a three-dimensional system, so you had x, y, z, and you had a single repeated eigenvector that had a multiplicity of 3. So we need 3 distinct linearly independent solutions off of a single eigenvalue, right? So we use the first one. It turns out this is the form. You're going to have a term on the end that has e to the lambda t. You're going to have a term here, which is t e to the lambda t. And then you're going to have another term, which is t squared over 2 e to the lambda t. And this will be the initial eigenvector. And then you'll find p, you'll find this eigenvector from using this eigenvector in the procedure. And then you will find this eigenvector from using this eigenvector on the right-hand side. Okay? So this is extendable, and the term form gets a little different as we go. We're not going to go above 2 in this class because it's already challenging enough to compute all this in a reasonable time frame. But just it's good to know that that does exist. And just to show you how this works, I'll do one example here to finish up. That's a multiplicity-free example. So let's say you had this three-dimensional system right here. We want to find the eigenvectors for the matrix. So eigenvalues for the matrix first. So we put the lambda on the main diagonal, we solve. We need to do the determinant, so I'm going to go ahead and choose this column here, right? We're going to go plus, minus, plus, because that way I have zeros, and I really only have to take this times the determinant of this. So 2 minus lambda times 2 minus lambda times 2 minus lambda minus 5 times 0. And then I've got minus 0 times some determinant, but that's just 0, plus 0 times some determinant, so that's just 0. So we end up getting 2 minus lambda cubed equals 0. So lambda is positive 2, but it has a multiplicity of 3. Okay, so what we would do is first find the original eigenvector. So we'll take 2 minus, I'm subtracting that 2 here now on the main diagonal from the coefficient matrix. And we're starting with zeros on the right-hand side for the normal eigenvector. When we do RRAF, we end up getting this. Now this is interesting. It gives me that this equation is 0 equals 0. This equation is K3 equals 0, and this one is K2 equals 0, and K1 is really not specified anywhere. So what that means is the solution form is that the K3 and K2 have to be 0, but K1 can be anything other than 0. We can't have a vector of 0 length. So I can just choose 1 for the K1 and then 0, 0. So 1, 0, 0 is our is our resulting vector, and this goes with lambdas too. Okay, to get the second vector, what we're going to do is we're going to replace the right-hand side here with what we got before. Since we chose 1, 0, 0, we will redo the eigenvector calculation using the same first three columns, except with 1, 0, 0 for the right-hand side. When we do RRAF, now we get that P2 is equal to 1 and P3 is equal to 0. So that means that P1 again can be anything, but P2 specifically has to be 1 and P3 is 0. So I could, this has to be a 1, that has to be a 0. I could choose this to be anything, might as well make it a 0. As long as it has a non-zero length, we're good. So I'm choosing 0, 1, 0. We could also have chosen 10, 1, 0 or negative 50, 1, 0. This could be anything. I'm just choosing it to be 0. You just need to make sure that the entire length is not 0. All right. So next we're going to need a third vector because we have a third degree here. So that means we're going to redo the procedure again. This time this right-hand side will be whatever we chose in the previous step for our last eigenvector. And when we do RAF on that, we get that Q2, so this is now called Q. Q is equal to negative 6/5, and Q3 has to be positive 1/5. So those two are established. And since Q1 is not specified, this can be anything. Might as well make it 0. All right. And then that means that the solution, now we're just going to use that form that's written directly. It's going to be the first solution is C1 e, and using our original vector 1, 0, 0. So C1, 1, 0, 0, e to the 2t. For the second term, we're going to use the one we just saw on the two-dimensional case. We're going to have a second term which uses the p vector. So we got k and we got k here. So it's going to be the 1, 0, 0 t e to the 2t, and then 0, 1, 0 e to the 2t, but with the p vector. That's all for C2. And then for C3, we're going to use this next form that I showed on the last screen, which is it's C3 times the k vector times t squared over 2e to the t2, and the p vector times te to the t2, and the q vector times e to the 2t. Okay? And that's really this system of differential equations. If you wrote it all really out, it'd be the first rows would be that the x's are C1 e to the 2t plus C2, t e to the 2t plus C3, t squared e to the 2t, and then these are 0. And then the y equation would be there is no C1, right, because there's 0 here. So C2, yeah, there's no C2 there, but there is a C2 here. So it's going to be C2 times e to the 2t, and then C3 times 1 e to the t e to the 2t minus 6/5 e to the 2t. And then the last row would be, there's nothing here, that's a 0, 0, 0, nothing there, nothing there. It's just C3, Z is 1/5 C3 e to the 2t. So this is the corresponding system of differential equations. That's the solution to the original system. All right, so that's how to handle repeated real roots. In the next video, we'll talk about how to handle complex roots. This should get us started for tonight's homework.